So I'm here in Puerto Varas, Chile, at the Cosmic Streams in the era of the Rubin Observatory Conference with one of the presenters, Mark Sullivan of the University of Southampton in the UK, who gave an interesting talk a couple of days ago, or maybe it was yesterday, on FBOTs, which are not, we don't see a lot of coverage in the media about FBOTs, which is one reason I thought this would be interesting because, and we're not even really sure what FBOTs are, but they're transient events. For first, Mark, tell us how do you define a transient event, and then what an FBOT signifies. It's a faint blue optical transient.
Yeah,
Correct?
that's right. So, yeah, my talk was on transients. The conference is about transients, and in particular, I'm talking about supernovae or cosmic explosions. So, objects that appear in the night sky that weren't there before. I was particularly focusing on those that explode in other galaxies. So, we're not talking about things that explode in our own galaxy. Now, these FBOTs, as you say, fast blue optical transients, are incredibly luminous events that don't last very long at all. So while a typical supernova, say an explosion of a white dwarf star, might last a few weeks and be about 10 billion times as bright as the sun, so pretty bright, these FBOTs are much faster. They appear and disappear within a week. They can be about the same brightness, they can even be brighter than the white dwarf explosions. And they're a real puzzle because they appear and disappear so quickly. It doesn't give astronomers very much time to study them in detail and figure out what they are.
And what are your best? What are the leading ideas about what they could be?
Well, most supernova explosions are powered by the radioactive decay of nickel 56. So when the supernova explodes, there's nuclear synthesis and a lot of nickel is made. This nickel is radioactive and it decays into cobalt 56 and iron 56. And that radioactive decay heats the supernova ejector up, the stuff that's thrown off in the explosion, and makes it glow and makes it very hot. Now, these FBOTs almost certainly are not powered by that mechanism because the decay of the light curve is just too rapid to be powered by this nickel.
And and explain what you mean by the term light curve.
So light curve is how the brightness of the supernova or FBOT changes with time. So it goes from 0 before the explosion, rapidly rises in its brightness, and then decays away. And that entire evolution of brightness is called the light curve.
Okay, and you were getting back to what could possibly
what these things
theoretical.
might actually be.
Yeah.
But there's a few ideas, and I would say actually in some cases we don't know yet. One idea is that the supernova explosion happens inside what's called circumstellar material.
Right.
So this is material that is thrown off during the star's life, but stays near the star. And then when the supernova explodes, it runs into this ejector, heats it up, makes it very hot, and a very luminous transient can result. So that's one idea.
Uh-huh.
Another idea is that it's the death of a massive star, and one of the things that can be left behind after the death of a massive star is a neutron star. Now, some neutron stars are very, very rapidly rotating. It's called magnetars. And as they lose their rotational energy, so as they slow down, they can also deposit a lot of energy into the ejector of the star that's left. That can also make a very bright optical transient. But the truthful answer is that in many cases, we don't know what these FBOTs actually are.
And how likely is it that the Rubin Observatory, over its observational lifetime of 10 years, probably be longer, I would assume, how likely is it that Rubin and then the follow-up study of these the alerts that it issues over these FBOTs, that we will understand over the next 10 years what these actually are?
Well, I certainly hope so. Now, we would hope that Rubin would find many hundreds of these types of transients because Rubin surveys so much sky to such a depth. It should find plenty of objects. But as you probably heard at this conference, the real trick to understanding what these objects are is being able to identify them in the data stream very quickly and very early. And when we do that, if we've got good candidates for these objects, we can send them to other telescopes and take spectroscopy. So spectroscopy is when we take the light from the supernova and disperse it, so break it up into its wavelengths. And when we do that, we can search for different chemical signatures of what might be in the explosion or the ejector. And that will help us understand what these objects are.
But
then we can compare them to different models.
But from start to finish, from the alerts have to be sent out within 60 seconds
Yep.
of actually the photons hitting the telescope, which is pretty incredible. Then the follow-up observations had to be done within 3 days or something
Yep.
like that.
Yep.
72 hours.
That's right. So we would want, so once the alerts come off the telescope, they will go to these brokers. So we've got lots of different teams around the world running brokers, and those brokers will be able to identify the really interesting objects.
And these aren't Wall Street brokers.
These aren't, well, no, they're not. So they're not quite as much currency in what we deal with. But these brokers will then identify the interesting things and allow us to trigger bigger telescopes in what's called target of opportunity mode.
And this is all, the brokers, let's be clear, are all automated, computer-generated filters.
That's right, they have to be, because there's just not the time for humans to get involved. Although it's quite likely that once the brokers have identified the most interesting objects in the data stream, a human could look at them before we trigger the big telescope. Then we trigger a big telescope to take a spectrum, and if everything goes well, that could be done within 24 hours of the object being detected by Reuben.
Well, thank you so much, Mark, for your time. We look forward to understanding some real data from these things once Reuben is online.
It's my pleasure.